All right, so what are the question we want to answer? What are the concentrations at equilibrium? Once it's reached, what do I expect them to be? And how are they related? Related to one another and to changes in free energy. So how they're related to one another is dictated by our equilibrium constant and how they're related to free energy change. Keeping in mind that what we're going to write is the free energy change for one half of this reaction, either forward, reverse would be with the negative sign. So let's write our generic reaction again. Some generic reaction. Now I'm going to use the lowercase nu to be stoichiometric coefficient. I'm following what the book does, okay, so the notation looks the same. Reactant A plus the stoichiometric amount of B that we need to react, forming some stoichiometric equivalent of C product and some stoichiometric equivalent of product D. Okay, all my nus are my stoichiometric coefficients needed to balance the reaction. And at equilibrium, the forward and reverse are both happening. So recall that free energy change, dG, is equal to chemical potential times the change in the number of moles. And so I can write this as, for the forward reaction only now, I have dG is equal to the chemical potential of A times the change in the number of moles of A plus the chemical potential of B times the change in the number of moles of B plus the chemical potential of C times the change in the number of moles of C plus the chemical potential of D times the change in the number of moles of D. So as a reaction progresses, change in free energy is the sum and the change of all the individual species. As the reaction progresses, change in free energy is the sum of the change of each species. So let's create a plot where we have 2A plus 1B making 1C and 2D. The example I alluded to earlier. Let's let the y-axis be change in number of moles. 0, 1, and 2. Negative 1, negative 2. Let's let this be 0. This is 1, representing the complete and full forward reaction goes to completion. We know in real life reactions are never, very rarely going to completion in the forward direction, but let's imagine they can, and we're going to call this x-axis the reaction progress variable, and we're going to give it the notation squiggle. This is, I don't know how to say this. It's xi. Who knows that Greek letter? It's like xi, psi, I don't know. And it kind of looks like a, I don't know, like a 3 with a line. Squiggle. So for this particular reaction, initially, we're looking at change in number of moles. Okay, so in going from the start of the reaction to the end, I am losing 2 moles of A. Right? So the difference in moles is going from 0 to, at the end, I have lost 2 moles of A. I have like a negative change in 2 moles. B, I started with 1, and at the end, I now have a difference of -1 mole of B. And on the other side, I'm making 1 mole of C. This is a horrible drawing. And 2 moles of D. Imagine these line up pretty. So what I can do is write my change in my number of mole term here, dN sub A, B, C, or D, in terms of the reaction progress variable. So the change in number of moles of A is equal to the stoichiometric coefficient that I began with, okay, times the change in the reaction progress. Okay. And there's a negative sign here because this is being consumed. These number of moles are getting consumed for the forward reaction.
Like officially just
For the forward reaction, these coefficients are not constants. And so we need to identify how they're changing with respect to the progress of the reaction. So the number of moles of B is also being consumed. We have some initial amount of B that we start with, times progress of the reaction. These are getting consumed, again, for forward direction. We could write it all for the other direction. We could have it all be backwards and flip all the signs. Change in the number of C, we're making C. And same with D, we're producing these. So these have a positive value. These are being produced. So what I want to do now is plug these relationships that I've written here. I'm going to plug these in. Plug this into the free energy equation written above, this sum of all the individual differences in free energy for each individual species to get a total free energy change for the whole thing. So plug us into the free energy equation above. dG is equal to, and then I'm going to also just pull the reaction progress variable out. So I have negative, I'm plugging in this term here for change in the number of moles of A. So I have my stoichiometric coefficient of A times the chemical potential of A. It's a negative sign because it's getting used up. I have my stoichiometric coefficients of B times the chemical potential of B. I'm making some stoichiometric equivalent of C, chemical potential of C, plus coefficients of D times the chemical potential of D. And all I've done is pull the reaction progress variable out of everything. Okay? It's in every single one of these terms because it was multiplied by the stoichiometric coefficient of each. If I'm at equilibrium, what is this equal to? 0, right? At equilibrium, dG is equal to 0. Okay, so when I set this all equal to 0, what I can do is move these terms all to the other side, and what I have now is stoichiometric coefficients of A times the chemical potential of A, plus the stoichiometric coefficients of B times the chemical potential of B are equal to a stoichiometric number of coefficients of C times chemical potential of C plus number of D use of D. Okay. The products of the chemical potential times the stoichiometric coefficient will be balanced at equilibrium for the products and reactants. And now what I want to do is write these terms here. I want to put these in terms of standard state. So the chemical potential of A in terms of standard state is given by the standard state chemical potential of A plus gas constant times temperature times the natural log of the concentration of A divided by the standard state concentration of A. But we know this is 1 molar, so we let it go.
I can look at